Today, 50 years ago, humanity landed on the moon. We have not gone further since. You can argue that there has been progress in other directions. Spaceflight has certainly become safer and more reliable since, but it will take a while for that to combine with the kind of progress we've seen back then. Since the end of the Apollo program, no one has gone as far out or seen those sights as the people who walked on the moon, and no one has taken as great a risk doing so as the people who first walked on the moon on the Apollo 11 mission. Which did of course take several days, but today is the 50th anniversary of the actual landing on the moon, which is certainly one of the greatest moments in human history. And of course there are many ways to celebrate this historic moment, and so I want to start this off with a few recommendations, because of course many people are doing something about this. If you're looking for something longer to spend the day with, there is a BBC documentary called Space Race. It's 4 one-hour parts, so about 4 hours. It's not perfectly accurate, of course, but it gets very close in the really relevant parts. It's a great documentary. For me personally, it's kind of a part of my childhood, because of course, being of a younger generations, I didn't get to actually experience a space race myself, but this documentary still, I think it takes on the space race nostalgia pretty well and communicates it. And if you search for it, you can find it on YouTube, though I'm not going to link directly to it, since that might not be strictly legal. Then of course there are other spaceflight related YouTubers like Scott Manley or Vintage Space, who do some minor explanation about something related to the Apollo program, which is basically what I'm doing too. And then, well, today there will actually coincidentally be an actual manned space launch to the ISS, which wasn't really planned for the 50th Apollo anniversary. It just happened to land on that day, actually due to being delayed from another day. Anyways, I'll be live streaming that, and after that I'll mirror on NASA TV, where you'll probably hear commemorative historic speeches from people much more involved in this than I am. But for now, let's get to the actual science part of this video. So I thought, since many things have already been done and other people are already doing most things, I might as well take this one thing and clear up a minor misconception that goes around and explain the details behind this. So what we're talking about today is the famous Plume suck-up or Plume suck-back from the Apollo launch footage, or that you see whenever a Saturn V launched. When it approaches Mach 3 or gets close to first stage separation around that time, so passing through Mach 3 at some decent altitude, you'll see that a plume of fire starts creeping up the side of the rocket, which seems to be part of the exhaust, and that is exactly the misconception I'll try to clear up with a bit of detail. Now, this has been understood before, and there have also been CFD simulations before, but I've never seen a proper in-depth explanation on YouTube before, and also I thought just for fun I might as well run a somewhat simplified but also somewhat detailed simulation myself. That is of course what you're seeing in the background right now. So the common idea is that due to the Saturn V flying at high supersonic speed at this point, a low pressure area builds up around the tail section of the fuselage, which is partially correct. It is a relatively low pressure section, but of course that's a common gas dynamics or aerodynamics misconception that a vacuum is somehow this super powerful thing, No, a vacuum is just as powerful as the outside pressure it's taking away. So a vacuum doesn't magically suck things up with infinite power. It just means that there's nothing opposing the surrounding pressure from elsewhere, which at this altitude isn't incredibly high. But yeah, there is a low pressure area around the tail section and of course behind the backplate of the Saturn V, between the engines and the bottom of the fuel tanks, since it is basically a blunt bottom going at high speed. There's an extremely low pressure area there where air flows in turbulently, causing a bit of drag, but actually not all that much, and a rocket is very heavy compared to its area, so it doesn't have to worry that much about drag. Now, the common explanation is that due to the suction and due to the exhaust from the sea level optimized rocket engines over-expanding at this altitude, the exhaust gets sucked back up and along the sides of the rocket. And that is not entirely true. That's not exactly how that works, which is actually kind of obvious if you look at it a little bit more in depth and try to understand it, which is of course what I usually like doing. There's just not enough energy in that. Like, if you under-expand fuel, you do waste a bit of energy, and there is a bit of energy left in that fuel. But if you just look at the ratio of specific impulse between a sea-level optimized engine and a vacuum optimized engine, or at the thermal energy left in the exhaust, you can easily tell there's not enough energy in this exhaust for its overexpansion to actually stop it and start moving it back upwards. And there's also not enough air around to slow it down in time without also cooling it down so much that it no longer wants to accelerate upwards again. So really there's no mechanism by which large amounts of exhaust would start creeping back up the rocket. There is of course a bit of turbulence going on and some mixing between air and exhaust, so tiny amounts of exhaust do get sucked back up actually, and soot from the exhaust mixes with the air, which of course makes the air more likely to glow because now it has solid particles in it. But most of what you see creeping up the sides of the rocket there is actually just air. So what basically happens is the air streaming along the sides of the fuselage as it reaches the tail of the rocket, where it suddenly stops in this blunt backplate and then reaches the engines. That air gets turbulently sucked behind the rocket and basically stops there for a while. So the air that streamed along the fuselage of the rocket is now stuck between the engines, essentially, and by being so close to the engines and the exhaust, it gets heated up. And since it partially mixes with the exhaust and the soot from the exhaust, it starts to glow as well. And that heated up air, which of course to the naked eye now looks almost indistinguishable from the exhaust itself, that is actually most of what gets sucked back up along the sides, and what you see as this huge dart of fire creeping along the side, up along the sides of the rocket as it passes through Mach 3 and approaches first stage separation. Which of course makes more sense, since well, a blunt tail can slow down air streaming along the body to a relative velocity of almost zero and keep it captured behind itself for a while, whereas exhaust accelerating back upwards is just not really energetically possible, at least not for any significant amount. So really what makes the Saturn V so special in this regard, and the reason why you see it with the Saturn V, and sometimes in parts with the space shuttle, but not so much with other rockets, is primarily because the Saturn V is so big that the air gets stuck between the engines for so long that it actually has time to somewhat heat up by being so close to the exhaust, so much that it actually starts glowing and starts looking like exhaust itself. So while the under-expansion and post-expansion of the exhaust and the low-pressure area around the back do have something to do with it, it's not actually as much an example for weird exhaust behavior as it's more an example for just the aerodynamic effects you get with fast-moving objects, high supersonic moving objects, with blunt tails or cavities where the air basically slows down to zero and gets heated up partially by its own energy, partially by being close to something hot, which is a rather interesting effect that can be quite a problem for supersonic aerodynamics in general. Although in this case it's not really that big a problem because, again, the Saturn V is really heavy. Aerodynamic forces relative to its mass are relatively small because it's huge. It has a large mass to surface area ratio, so making it a functioning, efficient rocket was more relevant than making it aerodynamically ideal. Hypothetically speaking, the way to prevent this would have been to give it a not too pointy, but a somewhat sloped, pointy-ish curved tail, which the engines then stick out of, kind of like radial engines, which would of course have made the whole design a lot more complicated, a lot less efficient, a lot heavier, and saved a tiny bit on drag, and that really wouldn't have been worth it. And the whole plume creep thing with fire, or what looks like exhaust creeping up the side of the rocket, wasn't really a problem either, so no reason to do anything like that. Instead, stick with a blunt bottom as they did. This also made it easier to get the engines to work well, since, well, a bottom-attached engine with some hot, turbulent, but also low pressure and slow-moving air around it is more predictable than a radial-mounted engine with regular density air streaming along it on one side at supersonic speed. And of course, getting the engines to work well was basically the main priority of the Saturn V design. So I hope you found this one little in-depth look into one tiny detail of the Saturn V design and clearing up one common misconception somewhat interesting. If you want a more broad historic overview of the Apollo program, there are other people better at that. Instead, I hope to get around to a few more in-depth physics explanations in the future. For today, basically on the minute 50 years after the first moon landing, I have scheduled a little Kerbal video to release, which I thought was a somewhat funny idea related to the Apollo program, and a nice idea for how to use the new Breaking Ground robotics parts. And of course I'll be live streaming the Soyuz launch today and the NASA TV Apollo 11 anniversary programming afterwards. And with that, see you later, and thanks for watching.